Hi, Physics 2 class. Today's lesson, we want to go over just a couple of random topics, and these will be topics that will be covered on the next quiz. Most of them are on the problem sets at some point, so a lot of terms that you will need to know, but some of these are not covered in problem sets, but yet will still be quizzed on, and the AP still asks some questions on these as well. Okay, well, we have covered refraction for several class periods now, so you guys should have a pretty good idea on it. So as of this point, we've had the terms reflection, refraction, we've talked about polarization, and now we need to introduce the term dispersion. When light enters a more or less optically dense medium, we should know that it refracts by now. So if we're looking at this picture of a prism right here, light comes in at an angle and then bends towards the normal as it goes into this glass prism. When we have white light that enters into the prism, the light will disperse into all of the different regions of the spectrum. So dispersion is simply the separation of white light into its component colors due to diffraction. So dispersion is caused by diffraction. Now, one thing that's a little different here, we are used to just seeing on the problem sets like glass has an index of refraction of 1.5 and water is 1.33. That is true in a general sense, but the definition of index refraction, remember, is the ratio of the speed of light through a vacuum to the speed of light through a medium. Since all light has different wavelengths, that means, and different frequencies, that means they have different energies. So when white light enters into a more optically dense medium, the violet light actually bends, which this gives blue and red instead of violet, but the blue light bends more towards the normal, or away from the normal, sorry, has a greater angle of refraction than the red colors do. So the actual index of refraction of the glass block has a range. It's not just 1.5, it might be 1.52 for blue and it might be 1.51 for red. It's a small range, but at the same time it does exist. So when light leaves the block, so upon entering, the blue light's going to bend more away from the normal, the blue light is going to have a greater angle of refraction than the red. But as it leaves, the blue light's also going to bend away from the normal more than the red light's going to come in, or red light's going to leave as well. So what we get is this visual here, if you guys can see it hopefully on the video. You end up with your violet end of the spectrum and your red end of the spectrum is on top. A couple of other examples. And things that we use all the time, but we don't really think about it. And I don't think a lot of people use this function on your rear view mirror. I know I tend to forget about it, and then I get upset when someone's got their bright lights right in my eyes. But on our rear view mirrors, most of them are shaped like a glass block like this. They're kind of triangular shaped. Now they're thin, but this just gives a little bit more of a visual purposes here. But the wedge of the glass block will then have a silvered surface that allows all the light that strikes it to reflect. So what happens during the daytime is we have light coming from the car or from behind us. Let's say just, obviously we don't have headlights on. We will have a partial reflection on this first interface here. And then we will have a partial refraction. Most of the light that enters into this glass block is going to refract. You're only going to have a small amount that actually is reflected on this. Then you have another reflection off of the mirrored surface, but then you have a second refraction off of this surface to go to your eye. So you're not getting 100% of the light that's being reflected off of the vehicles behind you or the surroundings, but you're getting a majority of it. Now, at night, we want to be able to eliminate this light or a majority of the light that's coming from the headlights behind us. So what we want to do is change the angle of this front surface Now the incident beam comes in, and notice it's the partial reflected beam that is now hitting our eyes. You end up with a separate, your refracted ray ends up going up towards the ceiling. So next time you're in your car, try this out. Just change the angle and move the little lever back and forth at night to kind of see where the actual primary ray that is reflected off of the back surface is moving to. So during the daytime, once again, we want a majority of the light to reflect and refract to our eyes. However, only about 5% of the incident light is reflected from the glass surface, so we get a dimmer light that comes to us, but yet we can still see those behind us. We've already talked about this part in class. We've already discussed that refraction causes the image of whatever is in the water to appear like it's higher. So once again, if you look here, there is your image of your fish. So the fish would actually be located lower down into the water than what we're actually seeing. So if you aim where the image is, you're going to end up shooting above the fish. But another thing that's interesting, and we won't get into the math in this, the AP doesn't ask us to calculate it, and it is kind of a pain in the rear. It's not too bad when you're directly over the object that is in the water, but if you have any sort of angle in it, this problem gets a little bit more complex. Not only does the image appear to be higher in the water than what it actually is, but due to the refraction, we also get a magnification of the object in the water. Like I said, we could trace out all the ray diagrams to show why this is, but anything that appears in the water is going to look like it's about 4/3 the actual size that the object is. So if you drop an object down the bottom of a swimming pool, you look straight down at the object, you will notice that the object appears to be a little bit bigger than what it actually is. All right, next topic. And everyone likes rainbows, so we have to talk about them a little bit. When we're discussing rainbows, it actually is a product of refraction, dispersion, and internal reflection. So those are all three different terms that we've had at some point throughout this unit. So the way this works, if we can consider that raindrops are perfectly spherical. Light enters from, so the observer's on the ground, so the sun will always be on this side and then the rain will be on this side, okay? Light comes in. Notice that the violet light and the red light start to disperse upon the initial refraction. But what happens on this back surface is, as light goes back from the water droplet to the atmosphere, it reaches the critical angle with respect to the observer and how you're observing that particular light. At the critical angle, all of that light is then reflected and then has a separate refraction when it comes out of the other surface and back to the air. So there's another refraction, and once again, the violet's going to bend more away from the normal than the red will. So the observer on the ground sees the range of the spectrum. Okay, but anyone that knows anything about rainbows and has seen these before, we should know that the red is always on the top of the rainbow, but this diagram shows the violet on the top and the red on the bottom. The reason this occurs is you are not seeing the entire range of the spectrum from just this raindrop. You need a lot of raindrops all stacked on top of each other in order for you to be able to see the actual rainbow form. So what happens is you may see the red light from this one, but then the violet light from one that's lower down in the sky. That combination of all of those different rays forms the rainbow that you actually see. You should be able to kind of think about it in how, the geometry works and why that makes the rainbows always curved. Based on the distances away from the particular raindrops that you're seeing. Last topic I want to talk about. This will only be conceptual on your test. We won't do any specific calculations here, but this is still interesting, and I've seen it pop up on multiple choice questions on the AP exam in the past. Brewster's angle. So we have talked about Malus law when we did polarization. but Brewster's angle is a little bit different of a topic here. So when the angle of incidence in which a particular polarized light source is when the angle of incidence with a perfect polarization is transmitted, there will not be any reflection when the angle of refraction and the angle of reflection add up to equal 90 degrees. And notice that the angle here is this between the reflected ray and the refracted ray. So let's back up here because I kind of butchered that statement up top. This ray here that's coming in, notice it has dots and the arrows drawn side to side. Okay, so this is unpolarized light. It's about the only way that we can represent it on a two-dimensional piece of paper. What happens when light reflects off of the water? That's why we get the glare off of the water when we're out on a boat or we're fishing. We get a lot of light that is reflected, and we talked about this when we dealt with polarizing sunglasses. The reflected ray that comes off of the water is polarized. The refracted ray is slightly polarized. Now, if I only limited this to a specific polarized light instead of being unpolarized, once this angle reaches 90 degrees, we can eliminate this reflection completely. Okay, a lot of our cameras now, we don't have to deal with it too much because everything's digital. Okay, but back in the day when we were using all lenses and had to adjust those lenses and take pictures, this did pose an issue in some things with the reflections because of the polarization of the light. Some locations you could be standing and you would get absolutely no reflection off of that surface because of the polarization on the reflection and reaching the Brewster angle when the light gets to the camera.